First, I want to emphasize the beauty and power of digital computing. If we want to do something else, we must also appreciate the good thing. Okay. So first thing to note is that digital computing didn't just appear on the scene invented by some technicians. It has a very long history, and it can be really traced back to Aristotle and his view on strict reasoning and compelling argumentation. From that source, there was an uninterrupted chain of philosophical and later mathematical thinking, ending ultimately with Hilbert, or a climax was Hilbert, who posed the question whether it is possible to formally prove every mathematical conjecture and whether there is a procedure for doing so. I will now briefly give an outline of the formal mathematical character of this question raised by Hilbert, because it was the key for inventing the Turing machine and later the theory of computing. So the question asked by, can you see my cursor? Okay, so the question was, is there an effective procedure for deciding every mathematical conjecture? So formally, mathematically, this can be translated into a crisp mathematical question. So what is a conjecture? It is going from some preconditions, call them axioms, to some claimed statement. And the question is whether there is a formal proof or whether one is entailed properly by the other. Formalizing the axioms and the theorem can be done in any mathematical formalism, and we will have a written down statement, a formal statement of this, where the axioms become strings of symbols, which can be listed in a list, and the question is whether the symbol string of the theorem follows from this. We can also concatenate the axioms and the claimed theorem in one symbol string and want to know, that's the question mark here, whether this is a true implication, yes or no. That's what we want to know about this string. Is it a good string or a bad string? This can be turned into numerics by coding this symbol string into a number. Famous name is Gödel numbering for this. So we have a code number for a mathematical conjecture, and we want to know whether it's a 0 or 1, true or false or true conjecture. So we have here a function, namely from code numbers, a numerical function from code numbers to 0 or 1. So that's just a function f, which includes all of mathematics, so to speak. If we could compute this function, we would know all about mathematics. It's a very interesting function. And even a bit more generally asking is the bottom line here, is there an effective procedure for computing every finitely definable function on the natural numbers? Among others, this mathematics all function. Okay, so that was the situation that Hilbert asked, and the question asked, and it could be formalized into a numerical function question, a mathematical question. And this was not answered by Hilbert. It was ultimately answered by Church and Turing in short succession, but the Turing answer became the more famous one. And the two actually knew each other very well. They worked together. And this is the Turing theory, and I will explain this very briefly. Turing added the final stone on this building of history. Namely, he gave a mathematical definition of what it actually means to be an effective procedure for computing any such function. That was not clear before. Much had to be said about this. But Turing sat down and thought, how can I formalize the notion of an effective procedure to compute a function? He came up with the Turing machine, and the Turing machine is a model. If you read his famous paper where he introduces them, is a model of a human mathematician sitting down with paper and pencil and reasoning. So the Turing tape is the paper of the mathematician. What is written on the tape is what the mathematician writes down. Then there is the mind of the human. That's the words that are used by Turing in this paper. The mind of the human is the finite state machine that controls the cursor that writes and reads and moves on the tape, which is the eye and the pen and the arm of the mathematician. And you could say the knowledge of the mathematician is cast into the transition table of this finite state machine, of its mind or his mind. Okay, so that's a Turing machine. And the important thing that I want to note, before I come to this slide, is that the Turing machine is a model of a human mathematician solving a problem with paper and pencil and thinking. And this in turn was a final, you could say, cornerstone or headstone for this 2000-year-old quest for finding out what can be done with rational reasoning. This, after Turing, developed into the full theory, textbook theory of digital computing that we have today, which I briefly outline here on this monster slide. It's not only the Turing machine today, it's a bunch of interconnected theories and formal models that all are glued together by symbolic structures. They are all discrete symbolic theories, and every computer scientist, after his or her studies, knows how to interrelate all of these theories to get a full range of practical theories that enable engineers to design microchips on the bottom, all through the programming and interfacing levels of building architectures, computer systems, and user interfaces, up to the formal model of semantics, of how to connect a process of computation to a formal task specification. All of this together needs to be in place to make digital computing the powerful thing that we have today. It's not only the Turing machine, but the Turing machine was the historical door opener for this theory building. Okay, so this is the summary. I will skip the bullet points and just bring home the basic message that computing as we understand it today is the essence of rational reasoning, so to speak. Well, that is how it evolved. Okay, so that was my appreciation of what we have when we speak of computing and admire the powers of digital computing. However, there's something which digital computing or symbolic computing is not. First of all, it's not a theory of the underlying mechanisms of what happens in the brain of the mathematician. Turing never uses the word brain, and he always says mind, connecting to philosophy, not to neuroscience. And if a computer science student reads a textbook, they will never find in their textbooks anything that relates directly to the hardware or to physics. And the word second that physicists need to describe reality is not mentioned in computer science textbooks. So it's a non-physical theory. And therefore, computer science really does not give us a guide to understand how one could exploit physical phenomena for computing, other than this little tiny effect that is used in digital computing, namely the stable switching between two symbolic states of a transistor, on or off. That's the only physics that's needed for building digital computers. Okay, so if we want to understand brains or build strange new neuromorphic machines or other unconventional machines, then we need something else and something more than the theory of digital computing. And we need to extend our concept of what computing is in the first place. So what we want, or what I want to help building, is a general formal theory, let's call it GFT, of computing system. And I put computing now always in, what are these things called, in quotes, because this means we are not talking about the same kind of computing that we are used to. It's not the same as digital computing. I could also say information processing, or I don't know what else I could say. I think we lack a word for the more general view of computing. So this GFT would be a formal mathematical framework that includes what we can learn about brains, but also what we can see in digital computers, but also in so many other physics-based computing approaches that are around and not so popular at this moment, but all have their little communities that are quite active. Actually, this morning, I was in a board, advisory board committee meeting for unconventional computing based on magnetic impulse transmission systems. So strange things happen, and it's but no one has a real good cue of how to formally mathematically think about these ways, and we don't really know what is computing in this general sense. So this is the last general purpose slide. Summarizing, digital symbolic computing is, in a sense, a top-down view on computing. It starts with the rational reasoning and drills it and boils it down until, in the physics world where the computers are built, one has to have something like transistors or other finite state switching systems. So Babbage's original mechanical computing machine also was a finite state switching machine. That's necessarily so. With other machines, you cannot do computing in this 2,000-year-old tradition. What we would want to have, or I would at least want to help making visible, is a bottom-up approach to understanding information processing or computing, starting from the physics, or if you wish, from what happens in brains, and then go upwards and evolve ways to see what can be done with those phenomena. So I'm certainly not the only one and not the first one who asks this question. In one of the papers that come, so at the end of this presentation, there is a list with a few papers that give more detail to what I'm saying here in high speed. There are numerous approaches, some historical, some are still active, where people have tried to come up with alternative stories about what is computing. Here I have a list, and none of them has so far become dominating or generally accepted. And if one looks closer, then one will find many reasons for shortcomings of each of them. In one of the papers that I cite here, at the end of this overview, you will find a more detailed discussion of these different approaches. So many people want to go for a general theory, a different theory and view on what is computing. And now I want to briefly outline my personal approach to this. That is my ongoing work. First of all, I think one set of good leading ideas can be obtained from the tradition of cybernetics. Cybernetics is also about in some kind of information processing. But compared to digital, it starts with computing, in quotes, embedded in real time and trained to its task. So this famous original, you could say, historical source of cybernetics is the governor. That's just a single proportional controller, we would say today. It works in real time and is directly connected to the task. It's not disembodied and does not do any rational thinking and then gives the solution and someone else has to do something with the solution. It's part of the reality in which it computes again in quotes, does its signal processing, so to speak. Because we are late in time, I will not try to explain the nice pictures on the left, the graphical pictures. Bottom line is it's online entrained and produces and is driven, such a computing or cybernetic system, by real-time signals, continuous signals, can be very high dimensional and very complex, and it produces likewise an ongoing stream of output signals. For instance, in a human, all the muscle activations or the speech signal that you're currently listening to. All of this is cybernetic, online, real processing stuff. So cybernetics is a very well established and strong both tradition and engineering discipline. It has some aspects that we want, or I want to see in a future formal theory of computing systems, especially its online entrained processing is, I think, important if one wants to understand how physical systems in general can compute. However, the mathematical groundworks behind cybernetic theories have difficulties with some aspects that we also need to understand real fully fledged computing in an abstract sense, especially multi-scale dynamics. It's my private hobby topic, and spatio-temporal phenomena in computing substrates are not natively covered by the cybernetic way of thinking, because it starts from signals, and especially from one-dimensional signals most of the time. Furthermore, there is no real formal model of what is computed in cybernetics. It's all about the mechanics and the Shannon information analysis of the signals that are being processed, but what they mean, how they relate to a task, is not part of what cybernetics can offer us. My claim is, or my idea is, that a full theory of computing also needs to have a semantic side part that tells us how to connect the computing processes to what is computed, to the task. So in one of these, in the fourth reference that I give at the end, I work out a contrast between a more generalized view on cybernetic-inspired computing theories versus algorithmic computing, that is the classical symbolic ones. On the left, you see three hierarchical description levels of a digital system. At the bottom, something like the binary switching dynamics inside a microchip, where you have, let's say, 8-bit registers, these vertical columns that switch their states according to the Boolean logic on a microchip. And going upwards in abstraction levels, such sub-processes are blocked into modules or functions until, after many, you could say, compilation and abstraction layers, one comes with a task description where the task is given by a user or a mathematician formally as a transformation task from some symbolic input structures, the block on the left, with some computation in between, to desired output symbolic structures. So bottom line in my wording, the classical algorithmic computing is all about processing structures. So at any point in time, if one looks at a computation, there are lots of symbolic structures around in the current state. And in the next moment, discrete hopping time, there are new structures. This can be traced back in history. I want to emphasize this again. Traced really back to Aristotle, where these update steps would be logical reasoning steps according to syllogistic reasoning rules or inference rules. In the cybernetic world on the right, there is no such thing as discrete hopping between symbolic structures. In contrast, one has input and output streams of data or signals, which can be quite richly structured. So this band structure that I tried to use here graphically should make this visible. And the input is coupled in real time with the output. And this coupling is now doing all the work. And we have to understand what can happen in such real-time coupling that transforms complex input streams into complex output streams, highly organized input streams to highly organized output streams. And in order to understand this, I think we need formal theories that can hierarchically disentangle or dissect such complex streams into substreams and hierarchically structure a global coupling of complex input to complex output into a network of increasingly finer resolved sub-processes, where in the end, at the very bottom, you meet physics, where one has physical variables, temporal variables, that would be the simplest signal streams that couple each other with physical coupling mechanisms, and there are very many physical coupling mechanisms that physics offers us. So a work out of this, if one really wants this, needs a lot of work. This hierarchy that I sketched on the previous slide is shown here in green in the middle. This would be a formal theory that allows mathematicians to describe such hierarchically nested streams of signals in a way that you have the freedom to abstract from more finely resolved levels of description to increasingly modularized and larger scale descriptions with exact mathematical transformations in between. So it's not just that that one has to have insight of a system engineer to know how a higher level of description should match the lower level one. There should be a mathematical translation between them. A short aside, in the neurosciences, much of the theoretical neurosciences is about this green part, understanding brains, where closer to physics here at the bottom, neuroscientists have fine-grained models, let's say of the biochemistry in synapses, And at the very high end, you have models of the global brain architecture, but people use different formalisms and do not really know how to connect these formalisms to each other when they work on different levels of abstraction. For an engineering theory, one would, however, need a glue to glue all of these levels of abstraction together and know what one is doing when one abstracts from one level to the other. Furthermore, I think what one also needs to have a really well-working formal theory of computing is what is shown in blue at the top here. This is a model of the task environment. So what can a computing system do? One needs a way to formalize such tasks and connect them to a computing system in two ways. So one would need to, given a task, how can we operationalize it, that it can be served by a computing system? And the other way around, if we have a computing system, how can we verify that it actually serves a given task? Both these red big arrows are known in computer science, in classical computer science. Program verification is known. It's known how to formalize tasks in logic. And it is, well, also known to a certain extent how to come from a task to a computing system solution, to a program, high-level program, although that part is not so easy and not automated. On the bottom, we also need a translation of an abstract computing system that is described at very fine level of resolution to physics. So we also need an interfacing between physical formalisms that the material scientists use to describe what's happening in their substrates with the lowest level of a computing abstraction, or computing this, should I say, model at the base level. Yeah, so I can at this point only just sketch that this is the set of tasks, the enormous set of tasks that theorists have to solve before I think we can come anywhere close with alternative approaches to computing, anywhere close to what the digital world currently just does all the time. So it's a long way to go, a very long way to go. Okay. In my own approach to this task, I make a few commitments. I briefly list them. One is I need a way to have a systematic way to describe a computing system on different levels of abstraction. So this is the computational model at level 1 up to computational model at level k. This would roughly correspond to compilation hierarchies, low-level programming to high-level programming or user interface programming in the digital world. But no time to say more about this. My approach to start formalizing such abstraction hierarchy building is that I view the formal variables in these models, the variables that denote the signal streams, as observers. So each of these variables looks at something that's happening in the abstraction level below. Yeah, that's all I can say here, given the very short time that I have. You can read, if you're interested, more about this in these cited papers. Okay, and I think, yeah, this is my last but one slide. To just give you a flavor of how this world of theorizing about computing in a different way might feel is given in these pictures. Picture A is digital computing. So it shows a little bit a microphotograph of a digital microchip, and at different points, contact points, you can record binary signal sequences, so on, off, and so forth. That is what's happening mathematically in a digital computer. In a, let's call it a material computing system or a substrate computing system, let's say a biochemical reacting system, the carriers of information could actually move. Think of a propagating wave somewhere. So then it's not just that at some point you have some signal, but the signal itself may wander and migrate. It may have spatial extension, it may have field character, and it may have different strength. Trying to visualize this with this colorful picture B. Another important difference to the digital view on computing is that one has basically unlimited freedom to interpret or to observe what's happening in the physical layer in different ways. So in this panel C, at the bottom, you see an electronic signal. And you can extract features or observables, formally define observables on it in limitless many ways. For instance, you could measure the white noise strength of the component in this. Then you get this green bar. In the beginning and the end, it's strong white noise. In the middle, it doesn't have white noise. Or you could add a sine wave filter, detection filter to this and have an observer that just looks at the sininess, so to speak. Then you would have a signal extracted from this physical source that looks like the blue line, or just at the signal energy, and so forth. So physics is open to interpretation and to observe whatever, in a sense, is observable. And that is not dictated by the physics. It's open to the designer of an information processing system. That is much more freedom than you have in the world of digital computing, where you only can observe and use switching phenomena. I want to highlight a cooperation that I have with a physics person, a microchip designer, Wilfried van der Wiel, in the Netherlands. He is building in hardware and investigating for unconventional computing so-called DNPU units. These are electronic devices that have many contact points. Here is an example shown with 8 contact points. Signals go in and out. It's actually each of these contact points can be used as input and or as output at the same time. And depending on the voltages that are applied at the input contacts, the currents at the designed output contacts can have all sorts of strange mathematical connections to the input signals. And this single device is highly flexible in what can be done with it. Just like neurons can do many, many things. And in different publications from the lab of Wilfried, you will find analysis and experimental demonstrations where these DNPU units have been used or, how should I say, exploited as Boolean circuits or as complex sets of neurons that replace several neurons in artificial neural networks and model the combined nonlinear responses of little neural populations. On the right, you see a graphic representation of what happens in reaction diffusion chemical reactions. All kinds of spatiotemporal phenomena occur there, which might or might not be used for computing. We don't know yet. No one really has a good idea how to use them. But they exist, they can be named, they can be observed. You can mathematically define certain phenomena in them. And who knows what could be done with them? Well, nobody knows, and that's bad, and we should learn more about that. Okay, I think we are done. This is my view on the state of the art in unconventional physics-based general computing. We have just taken off. So this is Blériot starting to cross the channel for the first time in 2009, I think it was. Maybe we are not even there yet. Maybe we are still pre-Lilienthal and try to get lifted running down a slope. We don't know yet. It's even hard to say how far we are.